Okay, this is the first video for chapter 13, which is the last chapter that we'll cover in this class. We're going to cover multivariate regression analysis, and it's going to be a fairly straightforward extension of the issues that we talked about in chapter 12. In this presentation, I'm going to cover the multiple regression model, and I'm basically going to concentrate on changes in notation that are required to keep track of more than one dependent variable. We'll also talk about how the least squares method applies to the multivariate regression case. It's a very straightforward extension, and I will end the discussion here by talking about the multiple coefficient of determination, which is basically sometimes also is called the adjusted R-squared. So we'll talk about the adjusted R-squared, why you would want to adjust the R-squared, and how to interpret the adjusted R-squared. We'll end with a discussion of model assumptions. These will be analogous to the model assumptions that we outlined and called the Gauss-Markov assumptions for the simple linear regression case. And then in the next video, we'll talk about topics that include testing for significance. And when I talk about testing for significance, it will be the F-test that I concentrate on. The t-test in the multiple regression model is exactly the same as it was in the simple regression model. So we'll cover that here, and it won't take too much effort to get to the t-test. The ANOVA table and the F-test will be a new topic, however. I'll briefly address the more complicated issue of estimation and prediction with confidence intervals in the multiple regression case. It's going to be that is a bit more complicated than in a simple regression case. I'll have a few comments to make about that. We've talked a lot in this course about categorical variables, so we'll talk about how categorical variables can be added to a regression analysis. And multiple regression analysis also gives us the opportunity to talk about nonlinear relationships and how to model those in a linear regression framework. So we'll talk about what it means to add a quadratic term to the regression analysis. Okay, we'll also talk a little bit about regression diagnostics and residual plots as well. So here, jumping in with the multiple regression model, this is a very direct extension of what we talked about before. We've got a population regression model where y is our dependent variable, and it depends on a predictable component of the relationship between that dependent variable and a number now of independent variables. So we've got an intercept term that's denoted by beta naught, and we've got p different independent variables instead of just one. So in order to keep track of the p different independent variables, we use these subscripts. So we don't just have a beta 1 coefficient, we've got a beta 2 coefficient, beta 3, beta 4 out to beta p, and so each x sub I variable is related to the beta sub I coefficient. That's really the only difference between this population regression model and the simple linear regression model. So again, we've got these different population parameters. They're fixed parameters by assumption, okay, and they're not changing. So these are not random variables. And now in order to express the relationship between the predictable component of the model and y with an equality, we of course have to add the error term. And the error term reflects the random variation that we would expect in y, even if we were to fix all the values of x and leave them at those values. So if we take the expectations operator through the population regression model, we will have the expected value of the error term equal to 0. So the expected value of y then is equal to beta naught plus beta 1 x1, beta 2 x2, etc. Okay, so what we're saying here is that we could fix the values of x hypothetically at given values and over again observe different outcomes of y at those fixed values of x, and it would change slightly from one observation to another simply because of that random error term e. But when we look at the distribution of those y values at those fixed x values, it's going to be centered on the expected value of y. right? And that's determined by the predictable component of the model. That's what we're saying here. So once we have our population regression model, we need to collect sample data in order to get point estimators of the various parameters of the population regression model. So B0 will be our best guess at the model parameter. Beta 0, B1 will be our best guess at the model's parameter of beta 1, etc. And we're going to assume that we have simple random sampling. That simplifies the analysis quite a bit. And we're going to use least squares to estimate all the different B's, and they will be our best estimates of the betas. So again, just to emphasize, the betas are not random variables, but the B's are, because every time we go out and collect a new sample, we're going to get slightly different B's as our estimates of the betas. So we'll think about the sampling distribution of these B's. Okay, so a schematic of what's going on here. We've got the multiple regression model. There's some true population relationship between this host of x variables, x1 to xp, and this variable y that we're interested in explaining. But we don't know what it is. So we're going to collect sample data. Hopefully we'll have a large sample. Large samples are nice. Although, if you have bad sampling techniques, you can have all the data in the world. No matter how big your sample is, you're not going to get good results if you have, bad sampling techniques. If you have bad sampling techniques and there's no way to fix it, there are methods for dealing with that at the estimation stage, but they're well beyond the scope of an introductory statistics class. So we've got a big data set, hopefully, and it represents a random sample. We're going to continue to assume that. And then we can go out and we can estimate this regression equation from the sample data. And when we estimate the regression equation, we'll use least squares. And then if the assumptions of the model are satisfied, these B's will provide good estimates of the betas. And by good, I mean that they'll be unbiased. And if all of the assumptions that are satisfied that we'll talk about at the end of this video lecture, if all those assumptions are satisfied, they'll not only be unbiased, but they'll also be the best linear unbiased estimators, or the most efficient way to estimate the betas. So the least squares criterion, again, is exactly the same as it was before, with the exception that I've got more x's that I have to account for when I calculate y hat I. So we still have basically the sum of the squared residuals that we're minimizing, except now that when we minimize, our choice variable set has been extended from 2, beta naught and beta 1, to p plus 1 different partial derivatives that we'll have to take. The derivative with respect to b0, b1, b2, b3, etc. up to bp. All of those partial derivatives, if you know anything about optimization, will be set equal to 0 and solve simultaneously for equations for all of these different betas. Sounds pretty complicated, but it's not really very complicated at all if you know multivariate calculus and you know matrix algebra. Neither one of those courses are prerequisites for this class, so I'm not going to go into any of the details here. Instead, we'll just use the computer software package, something like Excel, or if you prefer, like myself, something like Python, then you could use that in order to estimate the different values of the B's. Okay, so that's the least squares criterion. I would highly recommend that if you want to move on in statistics or economics or econometrics, that you take a good course in multivariate calculus and a good course in matrix algebra. So the example that we're going to use is going to be an example that uses a sample of 20 computer programmers and their salaries. We're going to study their salaries. Their salaries will be the dependent variable, and we're going to look at how those salaries are related to years of experience, right, and their score on an aptitude test. So we think that both of these things should impact salary. And as a prior, I'm going to imagine that probably more experience leads to a higher salary, and a better aptitude leads to a higher salary. And we're going to measure annual salary in thousands of dollars. So here's the data, just a brief look at it. you can see that as is required, we have variation in both of our X variables, years of experience and test score, and here we have our salary. That data varies also. That's what we're going to try to explain. So salary is our Y variable, and experience and test score will be our X variables. So we're going to let the first X variable be years of experience. Right, so years of experience is here, and the slope coefficient will be beta 1 associated with it. X2 will be our aptitude test score. So beta 2 will be the slope associated with that. And here's Y. Y is our salary measured in thousands of dollars. E is our error term. So this is our population regression model. We're going to try to estimate this, or we are going to estimate this, with least squares. So when we estimate it, I put all the data into Excel, and I ran Excel's regression package, and I came up with this table. So there are a number of things in this table that you're already familiar with. Lowercase n is the number of observations, and that's clearly equal to 20. Okay. The standard error of the estimate, which is the square root of the mean square error, is 2.418. Now, we haven't talked much about the ANOVA table, and we'll talk about that more in the next video. But you can calculate that. You already know that you can calculate that as the square root, right, of the mean square error. So, you know, the error or the residual is here. So the mean square residual of the mean square error is 5.85. So if you take the square root of that, you should come up with your 2.418 standard error. Okay, you're also familiar with the R squared. We'll cover that again briefly in a moment. And you're familiar with all the coefficients. So the coefficient 3.17 is the intercept term. Coming down here, I'm building the estimated regression equation. Okay, so salary is equal to the intercept term plus 1.404, kind of rounding there, times experience, right, is the experience variable, and then adding in linearly the impact of test score, right, aptitude test score. The coefficient there is 2.50 right here. Okay, so we have our estimated regression equation. You should also be familiar with the standard error. The standard error is the standard error of the sampling distribution of the associated coefficient. So the t-statistic is the ratio of the coefficient to the standard error. We learned about that in the last video. So for example, if I take 1.403 and divide it by 0.198, I get a really big t-statistic of 7.07. If I take the 0.25 coefficient and divide it by its standard error of 0.07, I'm going to get the t-statistic, another good-sized t-statistic, of 3.24. So this t-statistic is used to test the null hypothesis that the coefficient's equal to 0 against the alternative that's not equal to 0, that two-tailed test. So this p-value is consistent with a two-tailed test. That's the two-tailed test that we talked about in the last video. Nothing has changed here. So you can see that the p-values on experience and test score are very, very small. In fact, they're smaller even than 1%. So we can reject the null hypothesis even at a 1% significance level. In other words, if we reject the null hypothesis, we're taking less than a 1% chance that we're concluding that we have a significant relationship when we don't. So those are pretty small p-values. So there's some pretty some variables here on the right-hand side of the equation that seem to be really important for explaining our dependent variable, which is salary. What shows up over here is just a 95% confidence interval for the coefficients. I won't talk about those too much here. So we understand everything in this table, and what we want to, we want to extend our discussion to explain the adjusted R squared. I'm going to do that in this video. I'm going to do that, and in the next video, we're going to explain this ANOVA table and the F-test. That'll come in the next video. So interpreting the coefficients briefly before we move on to the topic of adjusted R squared, we've got beta 1 here. Beta 1 is 1.404, and the way that we interpret is that if we hold programmer aptitude test scores constant, an additional year of experience leads to a $1,404 increase in expected salary. So you have to remember that salary is measured in thousands. So, you're translating this into from thousands, right, into dollar, given that that's measured in thousands, the dependent variable, 1.404, you know, thousands is going to be $1,404. So it's $1.404 thousand dollars, or $1,404. Guess that's the best way to put it. And then again, same thing for the 0.251, right? If I hold experience constant, right, then an additional point on the aptitude test score is going to lead to a $251 increase in salary. So again, 0.251 thousand, dollars is $251. Now I'll say this also. If you want to understand the relationship between, let's say you want to understand the relationship between here, B2, which is the test score, okay? So you want to understand the relationship between test score and salary. Maybe you're not really all that interested in the relationship between, experience and salary. You really want to know the relationship between test score and salary. But both test score and experience influence salary. Then in order to accurately estimate the impact of test score on salary in a regression model, you're going to have to include both of the variables. That's going to be true anytime there's any correlation at all between test score and experience. Okay, so as a general rule, we don't want to add variables to the model that we don't need. But at the same time, if we leave out a variable from the model that's important for explaining the y variable, it really belongs in the model, but we don't include it, and it's in any way correlated to the variables that we do include in the model, we're going to bias the estimates of the impact of those included variables on the dependent variable. That's really important to understand. So it's more dangerous to leave a variable out of the model that belongs in the model than it is to add a variable to the model that shouldn't be there. Doesn't mean we want to add extraneous variables to the model, right? We don't want to overfit the model. Overfit models don't perform well. So we really need some way of determining when a variable should be included in the model and when it should not be included in the model. One way is just you can add variables and see whether or not they're statistically significant. But that can be somewhat dangerous because the model that you end up with could depend on the order in which you start adding the variables. There are a number of different ways of grappling with this. But one way is the adjusted R-squared, and we're going to talk about that next. Before we do that, I'd like you to answer a couple of questions on the checkpoint worksheet. Okay, welcome back. We're going to talk about the adjusted R-squared, continuing with the discussion we were having right before we took the break to answer the checkpoint questions. You'll recall that R-squared measures the percentage or the proportion of the deviation of y from its average variable that's explained by the regression model. And you'll recall from our computer output that was equal to 0.83. So 83.4%, roughly 83.4% of y's variation from its average is explained by a regression model. It's pretty good. One thing though about R-squared, when we're trying to figure out what the best model form is in terms of what should be included and what shouldn't be included in the model, is that anytime you add a variable, the R-squared is going to go up. Or if it doesn't go up, yes, it's going to go up maybe by just a really small amount or not at all, but it's never going to fall. So anytime you add another variable, the R-squared is not going to fall. So if we rely on the R-squared, we're likely to overfit the model and include too many variables. R-squared is really useful, but it's somewhat limited, right? We can't compare models that have different dependent variables using R-squared. And every time we add a variable, R-squared we know is going to go up, or at least it's going to stay the same. It's never going to drop. And so if we want to figure out whether or not we should add an additional variable to the model, we should have some measure of R-squared that's adjusted for the fact that we've included yet another variable in the model, because we don't want to overfit the model. Overfit models perform poorly, particularly for forecasting and prediction. So what we're going to have is an adjustment to r squared. Our adjusted r squared, with the a down here, the subscript that means adjusted r squared, is going to depend on the r squared that we've already talked about, but it's going to basically have a penalty for including an additional variable. So the improvement in r squared is going to have to be enough to offset the penalty that you receive for including an additional variable in the model. So I think what you can see if you look at this equation carefully is that if you increase p, if you increase the number of variables in the model, that is going to lead to a decrease, ceteris paribus, holding everything else constant, in the adjusted r squared. It's going to fall. You can see that because if p goes up, right, if p goes up, the denominator here, right, is going to go down, which is going to cause this term to fall, but I'm subtracting this for this, I'm subtracting this out, so it's going to cause the adjusted r squared to fall also. Okay, so when p goes up, n minus p is going to fall, right? This term is going to increase, and if this term increases, since it's being subtracted out here, the adjusted r squared is going to go down. So the increase in p here clearly leads to a decrease in adjusted r squared here. But an increase in r squared, because there's a minus sign in front of it here and there's a minus sign here, an increase in r squared is going to lead to an increase in the adjusted r squared. So these two things are kind of playing off of each other, okay? And so generally, if we include a variable and the adjusted r squared falls, we probably should think about not including that variable in the model. We'll see some practical applications of this later. So the adjusted r squared, you'll recall from the previous slide, is equal to 0.8146, right? So that's a that is a pretty healthy adjusted r squared. Now I'm really not going to compare the 0.8146 to the r squared here. What I would really want to do with r squared is compare the adjusted r squared, maybe with and without the experience variable, or the adjusted r squared, with and without the test score variable, and see whether or not the adjusted r squared itself rises or falls between those different specifications. There's really no sense in comparing the r squared and the adjusted r squared for a given specification. So here are the assumptions of the multiple regression model that I want to cover. Very similar to what we talked about before. The model's linear in parameters. We've discussed that already. I don't need to cover that anymore here. Instead of having variation in the x variable, we need some variation in each one of the x variables. Check. Okay, this is closely related to another assumption that we'll get to in a minute, so I don't need to spend too much time on that right here. We have random sampling. Okay, so we don't have any sample selection bias or anything to worry about. And like before, the covariance between the error term and every single x variable is now equal to 0. Okay, we talked about that in the previous video too. Right, the conditional, the expected value of the error conditional on the x values is equal to 0. Zero conditional mean, sometimes is what that's called. The conditional mean of the error is equal to 0. The covariance between the error term and the x's is equal to 0. In other words, we don't have anything in the error term that's predictable based on the x values. Also, assumption 5 is that no x variable is a linear combination of other x variables. So if one x variable can be expressed as a combination of other x variables in the data matrix, then you're not going to be able to complete least squares regression. If they're perfectly collinear, actually the entire estimation routine will fall apart. It's kind of hard to explain why without matrix algebra, but when you have the matrix, this array of all of the variables combined is sort of a data matrix, you have to perform an operation on that data matrix called inversion. You have to invert it in order to get the least squares estimate. And it's not possible to invert a data matrix if any row or column is a linear combination of other rows and columns. I'll kind of leave it at that, and we'll talk about it a little bit more when we talk about we'll talk about collinearity a little bit more when we talk about categorical variables, because it's a nice place to sort of introduce the intuition behind multicollinearity. But really, you don't want your dependent variables, if possible. You want them You don't want them too highly correlated with each other, because the more highly correlated they are with each other, the more difficult it is to parse out the individual influence of any one of those variables on the dependent variable. They can be highly collinear, and you can still complete the estimation. But if they're perfectly collinear, it's going to fall apart. The variance of E, again, is going to be denoted sigma squared, and it's constant and unrelated to other values of E. That's what I called before, that fancy word, the homoscedasticity assumption. We're going to assume that that continues to hold. If 1 through 5 hold, your estimates are unbiased. It might be okay for prediction or something, okay? If 6 also holds, not only do you have OLS is unbiased, you also have ordinary least squares. Our method is also best linear unbiased. In other words, it's the most efficient way, the minimum variance way of estimating the beta coefficients. Okay, so this homoscedasticity, that's pretty important stuff. If you don't have homoscedasticity, you still have the coefficient estimates are still unbiased. They're not the best linear unbiased estimates. And then finally, to complete hypothesis tests in our framework, we're going to require that E either be normally distributed, right, so that the T statistics and the F distribution, they'll apply exactly, or if the error term weren't normally distributed, we could have a very large sample, and if we had a large sample, the central limit theorem would cause the sampling distributions of the B's, our estimates of the betas, to become normally distributed. And so in a really large sample, you don't have to worry so much about assumption number 7, but you have to worry about it in a small sample for sure. Okay, so these last two are really most consequential when you're doing hypothesis testing. I'll leave it at that, and if you want to know more, I highly recommend taking a good econometrics course.